Okay, I want to continue our discussion of partial fraction expansions. And in this case, what I want to look at is what's called the repeated real roots case. Now, in order to do this, we're going to be looking at a problem something like this right here. We're going to say, suppose we have our function that we want to expand in partial fractions, f of s, that looks something like right there, that expression, and that it has a simple numerator, s plus 3. The denominator has three terms in it, s times s plus 2 times s plus 5, except that the s plus 2 term is squared. And that's what they refer to as a repeated root. It's a factor that appears more than once in the denominator. To do that, the partial fraction, the first thing we do is we write it like this. We write it as a1 over s plus a2 divided by s plus 2. Now here's what's different. a3 divided by s plus 2 squared plus a4 divided by s plus 5. Now we want to find the values of a1, a2, a3, and a4. Now the simplest way of doing this, of finding those values, uses calculus. But we're not there yet, so we have to do it a different way. So to begin, what we do is we take this equation right here, where we have this on the left side and this over here on the right side. We take that expression and we multiply through on both sides by the term that's in the denominator, s times s plus 2 squared times s plus 3. Multiply both sides, and this is the expression that we get. Okay, now when we do that, notice that this whole term right in here cancels with this whole term right here, leaving us with s plus 3 on the left side of the equal sign. The right side gets a little bit more interesting, where when we're multiplying this whole term times this first element, a1 divided by s. So in that case, just the s's cancel out, leaving us with s plus 2 squared times s plus 5 times a1. Now when we multiply this whole expression times the term a2 over s plus 2, the s plus 2 cancels from the denominator, but only one of the s plus 2's cancels in the numerator. That leaves us with s times s plus 2 times s plus 5 times a2. Now when we get to this term right in here, we have a3 divided by s plus 2 squared. This term will cancel with this term completely, leaving us the result s times s plus 5 times a3. And then finally, the fourth term here works in a very similar fashion. The s plus 5's cancel, and we get s times s plus 2 squared times a4. Now what we do is on the right side of the equation, which is now already pretty long, we expand all of these terms with the s plus 2 squareds in them, and we collect similar powers of s. So when we do that, we get an expression that looks something like this. S plus 3 on the left remains unchanged, but we get a whole term, a whole coefficient times s cubed. We get a different entire coefficient times s squared plus another one times s plus a constant term. So we have s plus 3 on the left must equal this times s cubed plus this times s squared plus this times s plus 20a. Now, so we have a polynomial on the left, a first order polynomial, equal to a third order polynomial on the right. Now, the only way that two polynomials can be equal, the only way is if their coefficients term by term are all equal. In other words, the coefficients of s cubed are equal on both sides. The coefficients of s squared are equal on both sides, and so on. So when we do that, we notice that the coefficient of s cubed on the left is 0. So we say, okay, the coefficient on the left is 0, but the coefficient of s cubed on the right is a1 plus a2 plus a4. This is what appears on the right. So in order for these two sides of the equation to be equal, 0 must equal this right over here. So that sum must equal 0. Similarly, the coefficient of s squared must be 0 because there's no s squared term on the left. That means that this whole expression must be 0. A little bit different for the coefficient multiplying s, because this whole thing must add up to 1 right here. So we get 1 is equal to that whole thing right there. And then we get the constant here is 3, so 3 must equal that right there. So when we write all of this down, here is the set of equations we get. a1 plus a2 plus a4 is 0, and then this expression is 0, this expression is 1, and this expression is 3. So we end up with 4 equations and 4 unknowns, a1, a2, a3, and a4, that must all be satisfied. And we have to solve those equations for the 4 unknowns, a1 through a4. So that's what we have to do next. Now, what I'm going to be talking about, and I haven't talked about this in the class as yet, is that there is, in fact, a systematic way of solving sets of linear equations like this. And one way of doing it is to use the matrix representation and follow through with matrix multiplication and finding the inverse matrix and such. Now, to give you just a brief intro or preview of what we're going to do, what we do is we take all these coefficients. A1 is the coefficient of A1 is 1, A2 here is 1, A3 is 0, notice there's no A3 term here, and a coefficient of A4 is 1. Over here, the coefficient of A1 is 9, coefficient of A2 is 7, coefficient of A3 is 1, coefficient of A4 is 4, and so on. We do that all the way down. We write this sort of square of numbers. And we're going to write immediately to the right a column with A1 times A2 times A3 times A4. And then over here we write another column with all of these constants in it, 0, 1, 0, 0, 1, 3. Now what this means, what this notation means, is the first equation is 1 times A1 plus 1 times A2 plus 0 times A3 plus 1 times A4, and that all equals 0. That's what this equation is right here. This one says 9 times A1 plus 7 times A2 plus 1 times A3 plus 4 times A4, and that all has to equal 0. That's what this equation says. This one right here says 24 times A3, 24 times A1 plus 10 times A2 plus 5 times A3 plus 4 times A1, and that is all equal to 1. That's this equation, and then finally we get this last equation. So this is how we set up the matrix representation for this set of 4 equations. And we go through the solution, which I said we will be talking about. We'll go through the solution, and when we do that, we find that A1 is equal to this term, A2 is equal to this term, A3 is equal to that term, and A4 is equal to this term. Now, what I challenge you to do, and this isn't that difficult, is take these values for A1, A2, A3, and A4 and go back and plug them into these equations and try it with a couple of equations and verify that these numbers satisfy these equations. Okay, until next time.